Okay, so hope you had a nice weekend. We're going to start class 4 today. We're going to move on to a new language, which is an extension of RDFS, which is called Web Ontology Language, or OWL. Just to confuse things, not WOL, but OLW. So the last time we spoke about logic, we started to speak about this logic layer that we would need for the semantic web. And we're going to continue to talk about that today, but with a new language and in much more depth. So RDFS, as we saw in the last class, we have 4 main features: subclass, subproperty, domain, and range. Yeah, and we saw that in the lab. So we have a few other terms and features, but these are the core 4 features that we have. So today's topic, we're going to continue talking about this logic layer, but we're going to go into much more depth. Yeah. So RDFS is sort of like the tip of the iceberg, and now we're going to deep dive into this OWL language here. Yeah. So just to mention that the slides are on the homepage as well. They're already published in case you want them. So does anyone know what this animal is called?
It's not a zebra.
Not a zebra. No. It's kind of a zebra though. It's called a zebroid. So it's a half zebra or zebra. We say zebra. Some people say zebra. Half zebra, half horse hybrid. Yeah, so it's essentially the offspring of a zebra and a non-zebra equine, an equine being a horse type animal. Yeah. So for example, in this case, probably a horse. So we're going to use this example a couple of times in the class. Maybe later on we're going to look at it, but just to start with, here's an example of an RDF graph where we have that sac is of type zebroid, and we have that sac has a sire, which means father, essentially in equine horse terms, has sire Marty, and Zach has dam, which means mother, Leah. Yeah. Then we have Zia as sire Marty. And we have Zia as dam Leah. Again, sire is father and dam is mother in equine terms. What could we conclude about Zia or Zia? Is zebroid, right? So we could conclude because they share the same parents, if Zach is a zebroid, then Zia must be a zebroid. Are we sure about that? Is that 100% certain, that conclusion? It seems so, yeah? So we can conclude that Zia is also a zebroid, right? But if we come to think about how we can draw that conclusion, how we figured that out, it's not so straightforward. So what kind of reasoning did we use here to figure this out? Do we think it was inductive or deductive? Deductive, okay. Yeah, so we could say that this is deductive, right? I mean, it seems strange that it would be inductive because we've never encountered zebroids before, right? It's not like we saw lots of zebroids and developed this pattern that this was probably more a deductive process, yeah? Okay, maybe an inductive conclusion. Okay, well, the species is the same for the parents, and then some deductive confirmation. It's not so straightforward, I would say, to know what reasoning. One could argue maybe a mix of both, but there's definitely a deductive element here. So what kind of reasoning are we using here? We could say deductive mostly. Maybe we guess based on an inductive or abductive idea, and then we deduce that it seems sound. Yeah, it seems like it must be correct. So what sorts of assumptions do we make to conclude that Zia is a zebroid? What kinds of information do we use to conclude this is the next question. So you use probably the information that a zebroid as a zebra parent and a non-zebra equine parent. That's one thing. There's actually a lot of things here that we could say. So the first thing we could say is that we could try to propose that maybe what we're doing is applying this pattern. If X has same sire or father and dam or mother is Y, and Y is a zebroid, then X is a zebroid. But this is way too specific. This is not, I don't think this is what we're applying when we come to that conclusion. Yeah. It's sort of like very specific to this example that we would remember this sort of rule here: X dam Z1, X sire Z2, Y dam Z1, Y sire Z2, Y-type zebroid, therefore X-type zebroid. This doesn't seem to be what is going on in our brains when we conclude this. Yeah, we didn't remember the specific pattern because many of you never heard of zebroids before. Yeah. So what kinds of ideas or assumptions or definitions are we using to conclude that Zia is a zebroid? And why is this important? It's important because if we want, for example, machines to make similar deductive or to have similar deductive powers, they need to be told explicitly how to reason about this. So I would say probably we're not remembering this sort of rule here, yeah? Rather, what we're looking at maybe are more general definitions. For example, that sire is a subproperty of parent, dam is a subproperty of parent, okay? So this is still not enough to this is. If the Zoom, so lots of problems with Zoom this semester. Is it stuck on the first slide for everyone, or? Just me. I'm gonna assume maybe. Okay, it's okay. So if sire is a subproperty of parent and dam is a subproperty of parent, this is a start, right? It tells us that, okay, now Zach has parent Marty and Zach has parent Leah. Zia has parent Marty and Zia has parent Leah. And obviously we also need some information about the definition of a zebroid. How do we define a zebroid? We say that a zebroid has exactly one parent, a zebra, and a zebroid has exactly one parent, a knot. The symbol here will represent knot in the slides, a knot zebra and an equine. Okay, does it make sense? So now, have we stated enough facts or information to conclude that Zia is a zebroid? So what do we know now? Based on Zach having parent Marty and Zach having parent Leah, if we say a zebroid has exactly one parent, a zebra, given that Zach is a zebroid, Zach has parent Marty and Zach has parent Leah, what can we conclude? We can maybe put forward that either Marty is a zebra or Leah is a zebra. Yeah. Okay. And we also have that a zebroid has exactly one parent, a not zebra, and an equine. So what does that mean? It means probably one of Marty or Leah are non-zebra equines. Yeah, we don't know which one. We don't know which one is the zebra here, right? Intuitively, we also don't know that. However, there's a couple of other cases that we have to consider. So we've said that a zebroid has exactly one parent, a zebra, and a zebroid has exactly one parent, a not zebra, and an equine. We know that a parent can't be both a zebra and a not zebra. So that's logical. We can't assign that to both of them. Yeah, so one parent can't cover both of these. However, what we don't know is how many parents Zach has. Maybe Zach has 3, 4, or 5 parents, and maybe those other parents that we haven't given are the actual zebras and the non-zebra equines, right? So in OWL, we're never going to assume that our data are complete. Yeah, that's the first thing. That's called the open world assumption, which we'll talk about a little bit later. The other thing we're never going to assume is that these two things are distinct unless we can prove it otherwise. So maybe Marty and Leah are just names or identifiers for the same parent. Yeah. So for all we know thus far, all we have is one parent in common, at least one parent in common with Zia, and that could be a zebra. Would that make Zia a zebroid? No, because a zebra can have 2 zebras that are parents, right? So we need to specify how many parents Zach has, and we need to specify somehow that these 2 parents are different. Yeah. So what we're going to say now is that a zebroid is a subclass of equine. Equine is equino, I suppose. Does equino work? Probably it's Latin, yeah. And an equine has exactly 2 parents, yeah. So based on this, we know that Zach has exactly 2 parents, yeah. There's still one possibility left, which is that these are 2 names for the same parent, and that there's this other parent elsewhere that we still haven't defined that would block our inference. So the last thing we need to define is some way to say that Marty and Leah are 2 different entities. Yeah, they refer to 2 different animals. They're not 2 names for the same animal. So we finish with 2 things cannot be related by sire and dam at the same time. Yeah, so we say that these properties are disjunct. Yeah, we can't have something related, one thing related to or two entities related by sire and dam at the same time. So that really means that Marty and Leah must be different. It means that Zach, since Zach is a zebroid, Zach must be an equine. It means that Zach has two parents, and we know that these two are distinct. And now we have sufficient information to conclude all this. Yeah. Okay, so we never actually know. What's interesting about this is we never actually know if Marty is the zebra or Leah is the zebra. Yeah, we have no idea, but we can still conclude that Zia is a zebra. So which of these are expressible in RDFS? Can we express sire as a subproperty of parent? Yeah. Dam is a subproperty of parent? Yes. A zebroid has exactly one parent, a zebra? No. A zebroid has exactly one parent, a non-zebra, and an equine? No. Zebroid is a subclass of equine? Yeah. An equine has exactly two parents? No. Two things cannot be related by sire and dam at the same time? No. So what we can express in RDFS are these highlighted axioms here. So an axiom is basically a definition that we assume to be true, a premise. So we can define these axioms here. Sire is a subproperty of parent, dam is a subproperty of parent, and a zebroid is a subclass of equine in RDFS. And the rest we'll be able to define in L. So we're going to see these sorts of features in L. Yeah. So that's the language we're going to cover today. So zebroids. Okay. So in terms of defining zebroids and other stuff, not just zebroids, we're not defining a language just to define semantics of zebroids, but we can apply this to other settings as well, of course. Web ontology language, it's a standard. Its first version was standardized in 2004. A second version came along and extended it with certain features, and that was, I think there was like a version 2.1 that was published in 2012. Yeah, so it's been around for a while. It has some underpinnings based on description logics. I know you can't see this table very well. So there's a bunch of notation here, mainly for reference in the slides. We'll go through it as we go along. I'm going to use some symbols here and there. I'm not going to make it very formal a class, but we will use some symbols and I'll explain them as we go. They're very much based on first order logic. I guess you've all seen first order logic at some point. And based on set notation. So we'll go through it as we need them. For today, we're not going to jump too much into the formal stuff. We're going to learn the language through a running example. Anybody want to guess what the example refers to? Godfather. Yeah. Padrino, no? Padrino, yeah. So we have Vito, Carmela, Sonny, Connie, Fredo, Michael, Mary, and Vincent, the Godfather. So we're going to look at a family tree and we're going to apply some axioms relating to familial relations. So before we start to look at the example, we have to name two main logical assumptions that we have in L that we already spoke about briefly. So the first is called the open world assumption. So if we look at this graph, we can assume this to be an RDF graph, right? Vito has child Connie, Vito has child Sonny, Vito has child Michael. 3 triples, yep. So according to this graph, how many children does Vito have, would you say? So the obvious answer is 3. Do we know that? What assumptions are we making if we say 3?
The data is complete.
Yeah, exactly. The first thing we'd have to assume if we say 3 is that the data are complete. Yep. So what would that mean? It means that essentially Vito does not have other children that are named here. Yeah. So we do not assume that the data are complete in this setting. Yeah, we assume that the data are incomplete. So what this means is, how many would we say then if we assume that the data are incomplete?
3.
Yeah, we could say at least 3. That's a good proposal, right? So we can say here that Vito has at least 3 children. However, as mentioned, yeah, so Vito could have more children, right? Also, it's not quite has 3 children, has at least 3 children. Sorry, this is Vito has 3 children. Okay, so no, because we never assume our data to be complete. And then we could guess that Vito has at least 3 children. So this is the first assumption, open world assumption. We don't assume the data to be complete. So I know in the last lab, some people said, oh, I'm applying a domain or I'm applying range, but it doesn't say that it's a capital city or it doesn't. So the idea here is to apply inference. We're going to try to complete the data. We're not going to try to say this has to have something because we assume the data to be incomplete. Yeah, so it's very different from databases, relational databases in that sense. Yeah, we assume the data to be incomplete. under the open world assumption. So RDFS and I'll take an open world assumption. Anything not known is not assumed to be false. It's simply unknown. Without further information, Vito may have children that we don't know about, that are not described in the data. Okay, so why might this assumption be important for the web? So if we assumed that the data were complete, it would be useful because it would give us additional information. If we assume the data to be complete, then we would know if we have children for Vito, then Vito has no more children. So if we were working in a company and we had a database for maybe whatever size company, a large company, let's say, and there was a database, and the database had an employee table, and it had a list of all the employees, and we wanted to check if somebody worked at the company, what would we do? We would check the database. We would see, is their root or their name in the database in the employee table? And if they aren't in the table, what would we conclude? They don't work there, because we assume that table to be complete. So that they don't work there is based on the assumption that the table is complete. So it can be useful to assume that our data are complete. It can give us additional information. However, in the context of the web, how would we ever do this, right? So in general, the base assumption here is to take an open world assumption, to say that we can never conclude something from the absence of information like we could in the employee case. There are certain cases, or there has been work on closing locally closed world assumption. So let's say, for example, we're working in Wikidata. We know we have a complete list of Nobel Prizes of winners. Then in that case, we could say that for this part of data, that Wikidata should be complete, or a data set should be complete. But that's for other more advanced, that's kind of research level topic. So as a base assumption, we're going to take this open world assumption. We're never going to assume that data are complete. And the very detailed explanation here is that assuming web data to be complete is a bad idea, registered trademark. Okay, so our second assumption is called which is actually not really assumption. Actually, one could say as well, the open world assumption is not an assumption. It's a lack of assumption. We don't assume our data to be complete. It's the most general case. And here again, we have another lack of an assumption that one might automatically assume. We have no unique name assumption, which means basically that we never assume, unless proven otherwise, we never assume that these names, Connie, Sonny, Fredo, and Michael, necessarily refer to different entities, distinct entities. So this is called a no unique name assumption, or it's just a lack of a unique name assumption. So based on this, if these names could refer to the same entity, to the same child, how many children would we say that Vito has now? At least one. At least one, So if we combine both, we'll say it's incomplete, so it's at least, and all of these could be the same, there could be different identifiers for the same entity. So we say that Vito has at least one child. And this is what we know from these data here. Now, when we start adding axioms, we can start to actually get a finer estimate of how many children Vito might have. So we'll see that. But as our base case here, we say Vito has at least one child. So RDFS and OWL do not take a unique name assumption. Two or more IRIs may refer to the same thing. Without further information, the IRIs we know to be Vito's children may refer to one real world thing. Why might this assumption be important for the web? What if we were to assume a unique name assumption? Again, it could give useful information. It could give us that Vito has at least 3 children rather than at least 1. Would it be a good idea for the web? Now we'd have to assume that there's one IRI for everything, right? We'd have to assume that there's one IRI that everyone agrees on for Universidad de Chile, right? Who defines that? How do we get everyone to agree on the same IRI? What happens if we integrate data where they use different IRIs for the same things? We take DBpedia and we combine it with Wikidata, and we combine it with some data from the US government portal and from New York Times. All these data sets have some RDF data out there. We can't assume the IRIs to refer to different things, right? Because there might be overlap in what they're talking about. So it would be very difficult on the web to assume everybody agrees on the IRI to refer to a particular thing. So we're not going to assume that. It would make life a lot easier, but it would be very against the web architecture. The idea that there's some authority that says this is the IRI for this thing, and it's wrong to use any other IRI is completely antithetical to the web. There have been attempts at that, by the way, but they didn't really work out very well. Okay, so any questions about open world assumption? No unique name assumption? No, we're good. Okay, so we're going to go through the language features. So we're going to start with some RDFS, which we've already seen, just to get a flavor of what the examples are going to look like. So we have a subproperty of, and here I'm going to use like a default namespace, just a blank namespace like the EX thing we used in the last lab, yeah? So we have Vito, husband of Carmela, and if we say that husband of is a subproperty of spouse, what could we conclude from this? So Vito, husband of Carmela, and husband of subproperty of spouse would give us Vito, spouse Carmela. Yep. So just like this. Yep. And if we were to say Carmela, wife of Vito, wife of subproperty of spouse, Carmela, spouse, Vito, right? Yeah. Okay. Subclass of Mary, a woman, woman, subclass of person. There is a person. Yeah. Domain, Carmela, mother of Fredo, mother of domain, female. Carmela, type few. Range, Carmela has son Fredo. Fredo has son, range male. Fredo, a male. Okay. So that's RDFS. We're going to start looking at some new features now. The first feature we have is for equality and inequality of individuals. So we spoke about how we have no unique name assumption. We never assume things to be necessarily different. So in fact, we have this al same as, which allows us to say that two identifiers refer to the same entity. Yeah, so here in this case, we're saying Vito old is the same as Vito young. Now, one could argue that we might not want to actually claim this, but if we do claim it, what are we going to be saying? Essentially, if we have some, if Vito old is the same as Vito young, then Vito young is the same as Vito old. If we have A same as B, same as C, then we have A same as C, and we have A same as A. We have what's called an equivalence relation. So essentially, symmetric, transitive, and reflexive. Yeah. So this is a case of symmetry. Also, what's perhaps more interesting is if we have Vito old has grandson Vincent, and we have Vito young, Mary, granddaughter of Vito young. What could we conclude from this? So we could conclude Mary, granddaughter of Vito old, and we could conclude Vito young has grandson Vincent, right? They're somehow interchangeable. So what we can do is sort of smush these two entities together, and then we can kind of integrate the data and say that, okay, these are two ways to refer to the same thing. Now, we might make this axiom, we want to be maybe a little bit careful. If we're talking about somehow the person or the character, then, okay, it seems sensible to say that Vito is the same as Vito. The old version and the young version, they're both the same person. However, we'd have to be careful if we had Vito old, let's go back. If we had Vito old played by Marlon Brando, and if we had Vito young played by Robert De Niro, then it wouldn't be suitable anymore to say they're the same as, right? Because Vito young was not played by Marlon Brando, and Vito old was not played by Robert De Niro. Yeah, so we have to, if we want to say the two things are the same, what we're saying really is that anything that applies to one applies to the other. They're somehow interchangeable. Yeah. So in this case, one might argue, okay, maybe it's not something we want to do, but if we do that, this is the sort of situation where essentially now we have two aliases for the same entity, yeah, and they're interchangeable.
So if we wanted to keep the different actors, we would have to connect the granddaughter to both Vitos and the grandson to both Vitos?
Yeah, that's kind of awkward. What I would say you should probably do in this case, if you really wanted to distinguish these, would be to have a Vito entity and give all of the general information that applies to Vito to that, and then you could say Vito version old, Vito version young, or something like that, yeah, or portrayal or something along those lines. So I would add a Vito and then connect that, and then connect Vito with the old version and the new version. More questions? Okay. So if we have same as, one might ask, what about saying that two things are different or distinct? So we have Vito here has child Connie, Sonny, Fredo, Michael. Yep. And what we're going to say is that Connie is different from Sonny, from Fredo, and from Michael. Yeah, which we can use this property how different from to state that. So Connie is different from Sonny, Connie is different from Fredo, Connie is different from Michael. How many children does Vito have according to this RDF graph? Now? At least two. Yeah. So we know that Connie must be different from all the other three. But the other three can still be the same. Yeah. So we have Connie here, and then we have, well, this is difficult to do. We have Connie here, and then we have our three here. So like this. So we have Connie here, but these three could still be the same, right? So we know at least two. Yeah. And then we could have more. Okay, so Vito has at least two children. So we have our first case, something we didn't see in RDFS. It exists in some syntactic sense, but not really in a meaningful way. But what we can have in OWL is a notion of inconsistency, a notion of contradictions. So if we say that Vito old is the same as Vito young, and Vito old is different from Vito young, because there are maybe two people who disagree on this, or there's some inference that gives us something contradictory. What happens in this case? It's a contradiction. It's a clear inconsistency. These two things we cannot say at the same time. So we infer what's called false or inconsistency, and the world implodes as if we had divided by zero or something like that. So I'll come back to what this means a little bit later in inconsistency and why it's difficult in logics sometimes to manage these sorts of cases. And this is very common. This happens all the time on the web. Yeah, people disagree on things. They say contradictory stuff. Okay. So we're going to move to our first category of three categories. We have property axioms, class axioms, and then class definitions. And that will be the language. So our first set of features in OWL are, our second, because we've already seen inequality, our second of four are property axioms. So we have OWL equivalent property, which basically says that two properties are aliases of each other. Yeah, they're interchangeable. So if we have Vito parent of Michael, Michael has child Mary, and then we say parent of is equivalent property to has child, which kind of sounds strange, but if we think about it, they're the same. Yeah, parent of has child. It's kind of they're more or less aliases. There are two names for the same thing. So what could we infer from this? We can infer Vito has child Michael. Yeah. And what could we infer about Michael? Parent of Mary. Yep. So we can infer here that Vito has child Michael and Michael parent of Mary. We can also infer things at the schema level. If we say parent of equivalent property has child, it's equivalent to saying parent of subproperty of has child and has child subproperty of parent of. Yeah, it's like a bidirectional inclusion. Inverse of. So we have Carmela parent of Sonny, Vincent child of Sonny. So in this case, we're going to say parent of inverse of child of. Okay. So parent of inverse of child of. Yeah, what does this mean? It means it's the same property, but it goes in the other direction, in the opposite direction. Okay. So what can we conclude from this? What can we conclude about Sonny? Sonny is the child of Carmela. Yeah. What about what else can we conclude about Sonny? Sonny is the parent of Vincent. Yeah. Vincent. Yeah. So yeah, we get both of these inferences here. So Sonny is the parent of Vincent, and that Sonny is the child of Carmela. Yeah. So it works in both directions, the inverse. Yeah. So it's like equivalent, but we have to change the direction. Symmetric properties. You probably heard of symmetric properties before. No? So we can define a property to be symmetric here. We could say that if Connie is the sibling of Fredo, and if sibling is of type symmetric property, what could we infer from this? We can infer Fredo sibling Connie, yeah, which is completely equivalent to saying sibling type symmetric property is like saying sibling inverse of sibling. Yeah, it's the same thing. Yeah. So Fredo sibling Connie. Transitive property. You've seen transitive property before as well. You've seen transitivity before. Carmela, ancestor of Michael, Michael, ancestor of Mary, and we're going to define that ancestor of is a type transitive property. Yeah. So what would we conclude from this? Yeah, Carmela, ancestor of Mary. Yeah. So we get this transitive relation here. Property chain axiom. It's similar to transitive property, but we can have different properties in the chain, and we can also have a different property in the conclusion. So here, this is ancestor of, followed by ancestor of implies ancestor of. Yeah, we can do something similar, but with property chain, we don't need to have the same properties nor in the conclusion. So if we say Sonny is the brother of Michael and Michael is the parent of Mary, what could we conclude between Sonny and Mary? Uncle. Yeah, deal. Yeah. So we could say Sonny is the uncle of Mary. Yeah. So uncle of, how do we do this? If we want to do this, we can use property chain axiom and say uncle of, tío de, property chain axiom, brother of, parent of. Yeah, makes sense. And then when we look at this here, we are going to get Sonny is the uncle of Mary. If we wanted to be a little bit more general, no, we can't be more general. No, doesn't work. I was thinking this could be sibling of, but then it's not so, it doesn't work. It could also be aunt or tia. So Sonny, uncle of Mary. Okay. So if you see this 2 here in the corner, it's not really essential, but just for reference, if you see a 2 here in the corner, it means it's new to AL version 2. Yeah. So I'm not going to draw too much attention to it because of this at this stage, it doesn't really matter. Most reasoners support L2. Reflexive property. So this is kind of a strange one. If we think about materializing or creating inferences like we've seen in the labs, but we can say similar to is type reflexive property. So what's a reflexive property? It's something that holds to itself, right? So we could say similar to is a reflexive property, which means that everything is related to itself by the property similar to. Yeah. So what could we conclude in this case if we just have these IRIs, Connie and Fredo, are these entities? Connie is similar to Connie, and Fredo is similar to Fredo. Yeah. So this is a kind of a strange axiom to state, but it can be useful in combination with other definitions and axioms and so forth. It can give us some useful information. Everything is going to be similar to itself now. Functional property. So these are really useful if we're trying to integrate data where we want to figure out which sorts of things are the same. So we have here a relation has biological father. Yeah. So we have Fredo has biological father, Vito old. Fredo has biological father, Vito young. We're going to define based on this. In this case, we're going to take the axiom that has biological father is a functional property. What does that state? It basically tells us that has biological father is a function. What does a function do? It gives you one value. Yeah, one result. Yeah. So what does it mean? It means that essentially one person can only have one value for a functional property. An entity can only have one value for a functional property. Yeah. What does this mean? What could we conclude in this case based on these definitions?
They're the same, you know.
Yeah, exactly. So we can conclude rather than that there's an inconsistency here, we conclude that they're the same because we don't have a unique name assumption. Yeah. So without the unique name assumption, there's no inconsistency here. We just assume that these 2 entities refer, or 2 IRIs or identifiers refer to the same entity. What if we said has father was functional? Well, there's various problems that could be related for that. But for example, we have adopted Tom Hagen was the adopted son of Vito, so maybe he has 2 fathers. We could also have gay fathers and so forth. So wouldn't be so general. So we have inverse functional property. In this case, we have Vito old biological father of Connie and Vito young biological father of Connie. So what we can do is the opposite. We can use something called an inverse functional property, which is the same as functional property, but it goes in the other direction. Yeah. So what does it mean in this case? It means that these two guys again, Vito young and Vito old, must be the same. Yeah. Okay, weird example. I tried to think of more natural examples here, but for this particular setting, it's very natural in some cases. In this case, it wasn't straightforward to come up with an easy example. But we have a very useful feature called has key. So has key allows us to define that entities or instances of a particular class can be uniquely identified by a certain set of properties. Yeah. So in this case, we have Connie has biological mother Carmela. Connie was born on this date, and we have Constanza has biological mother Carmela, and Constanza was born on this date. Yeah. So we could say that all entities have as a key has biological mother and born. So the date they were born on and their biological mother should be enough to identify all entities except for twins. Yeah. So we're not done yet. So we say as well that they're singletons, which means just it's not even a good term in English. It just means they're not twins or triplets, or they were single lone births. Yeah. So if we satisfy all of these conditions, then we can safely say, what can we say? Connie and Constanza must be the same. Yeah. So Connie being a nickname or a short version of Constanza, effectively. So if we satisfy all of this information, then we could say intuitively that Connie and Constanza are the same. To formalize this, what we're going to define is that singleton, this particular class here, instances of this particular class here, have the key has biological mother and born, which is written singleton, al has key, and we use a list, has biological mother and born. Yeah. So now we know that these two entities are referring to the same thing. Irreflexive property. So we can say that has brother is an irreflexive property. Yeah. So you can't be your own brother. Although I don't know, maybe that's debatable. But you can't be your own sibling. So if we define that to be the case, and we have Fredo has brother Fredo, what does it mean? It means an inconsistency. Yeah. There's no way to resolve this. There's other than that this is a contradiction. Yeah. So the world implodes again. Asymmetric property, and we're getting there with the property axioms. Asymmetric property basically it states that, for example, we have here Fredo has father Vito Young, and Vito Young has father Fredo. So this might give us some alarm bells, and we might think this makes no sense, and this is a time travel sort of movie. This sort of situation does exist in certain movies, time travel movies, but Godfather, no. So outside of time travel movies, we could say actually this sort of case we don't want to have. We don't want to have A has father B, B has father A. It doesn't really seem to make much sense. Yeah. So what we can state in this case is that has father is a asymmetric property or asymmetric property, which means that we can't have this particular case here. If A is has father B, then and has father is symmetric property, it means that B does not have father A. Yeah. So in this case, we get an inconsistency. These things together form a contradiction. Property disjoint with is a similar case, but we can define two properties to be disjoint, yeah, that they can't relate the same pairs of entities. If we take all the pairs of entities related by property P1 and all the pairs of entities related by property P2, if property P1 and P2 are disjoint, it means that they can't relate any pair in common. Yeah. So in this case, we say has father. So we have Sonny has father Vito Young and Sonny has son Vito Young. So we could say that again, alarm bells, this seems to not make sense. If we want to formalize that intuition, we can find has son property disjoint with has father. Yeah. And this basically states that we can't have two pairs with the same relation like this. So in this case, again, we get the confusion of false and the world implodes. I think last of the property axioms is the negative property assertion. So basically it just allows us to state that something does not hold. It's kind of awkward, actually. If we look in the graph here, sorry, there's a little negation symbol here to say Fredo does not have mother Connie, and then it says Fredo has mother Connie. So it's a little bit difficult to represent the not in RDF because we have our triple and then we have to put a not somewhere. And the question is, where do we put the not? Because we've already used the three parts. So we have to reify it. We essentially have to create a new node that represents the triple, the assertion we want to negate. And then we can state the subject, the predicate, and the object of the thing that we want to negate. And sometimes we can also type it as a negative property assertion, yeah, which is optional. So stating that something does not hold in RDF or a triple doesn't hold is a little bit awkward. We need like at least 3 or 4 triples for that. Okay. So the way we write it in OWL is to say source individual Fredo, assertion property has mother, target individual Connie, and we can optionally type it as negated property assertion. But given that all of these properties are only used for negated property assertions, we can infer it from the domain of those properties. So all this says here is that Fredo does not have mother Connie, and then it says Fredo has mother Connie. And the conclusion here is that false, more than false. Yeah, so we can't say Fredo does not have mother Connie and Fredo has mother Connie together. It just, there's no way to resolve this. Okay, any questions about property axioms? You look good? Okay, so class axioms, super short. There's 2. First axiom is equivalent class. So we have Vincent type human and Mary type person. What might we want to say between human and person? That they're equivalent classes. Yeah, they contain the same extension. That if something is an instance of one, it must be an instance of the other. Yeah. So if we define human and equivalent class person, what could we say about Vincent? Vincent's a person. And what could we say about Mary? Mary's a human. So Vincent type person and Mary type human. I'm not sure if there's any argument against saying a person and human are not equivalent class. Maybe fictional, but fictionality applies to both equally. So either they're included or not included. I don't know. Disjoint with. So we can say that 2 classes have nothing in common, which is the kind of the dual case, right? So if we have that Vincent is a mafia boss and Vincent is a law-abiding citizen or a lawful entity, we could say mafia boss is disjoint with lawful, which means that nobody that's a mafia boss can be lawful, and nobody that's lawful can be a mafia boss. You can't be lawful and a mafia boss at the same time. Yep. One might argue that this is not the case, but okay, well, we're going to define it like that. And if we define it like this, what do we get? We get false. Yeah, because we do have here an instance of 2 disjoint classes. Yeah, so this is a contradiction in the world of floods. So we can take another example here. We have Vincent is a mafia boss and Mary is lawful. And we're going to define that mafia boss is disjoint with lawful. What can we conclude now about Vincent and Mary? Yeah, they're not the same. They're different from, right? So they're actually this thing. Yeah. So different from Vincent is different from Mary. And this is commonly, instead of stating different from, which we can do in certain cases, you will see these statements sometimes to distinguish entities that are commonly mistaken. For example, that Tokyo City is different from Tokyo, the province, right? So people might state it explicitly, but the majority of difference from statements are going to be inferred from something like a disjointness. They're going to be implicit. So that was class axioms. We have 2, which is equivalent class. This is equivalent again to 2 subclass of relations: A subclass of B, B subclass of A. That's the equivalent class, and disjoint with. So we have 2 features there. Any questions or doubts about that? Okay. Now we're getting a bit into the deep end for the last features. So we have class definitions in L. So here I'm going to start to use some of these symbols. I've left it here for reference, but I will explain them as we go through them. So the core idea of class definitions is we can define new classes based on properties and other classes and so forth. So thus far we created a class and we just named it as something, and then we defined axioms or made claims about it. Here we can actually define new classes based on logical expressions over classes and properties, and also individuals or entities in our data. So in this case, what we're defining is a new class. This is our class definition here on the right-hand side of this axiom. Our class definition is the class of things that are both female and parent. Yeah. So what does this symbol here mean? It's like intersection. So it's like a square form of the set intersection symbol. Yeah. And this one is like a square form of the subset or equal symbols. So this means subclass. Yeah. So this is subclass and this is intersection. So our class definition is here is female and parent, intersection of those. So we've defined a new class. That's the intersection of female and parent. And now we've said that mother is a subclass of this intersection of this new class we've created. Yep. So we have mother subclass of, which is an axiom, and then we have a class definition here in using a blank note. We have intersection of female parent. So we've defined here a new class that's the intersection of female and parent. If we say Carmela is of type mother, what could we conclude? Carmela must be type female, it must be a type parent. Yeah, it must be in the intersection of these two, so it must be in each of those classes. Yeah. We're going to change our axiom. So here we say subclass. This is a subclass relation. This time we're going to say, one could say, actually, doesn't it apply the other way too? Isn't this a subclass of this? Isn't this really an exact definition? So we can change our axiom to this symbol here, which is equivalence, equivalent class. Yeah. So instead of subclass here, we have equivalent class. So now we're saying that these two expressions are equal, that this mother class is precisely equal to the intersection of female and parent. Yeah. So if we state now that Carmela is a female and parent, what could we conclude? That Carmela is the mother. Yeah. Okay, in this case, we have person is equivalent to criminal or union lawful, right? So this symbol is like the union symbol, a square version of it from set theory. Okay. So what we're saying is that a person is equivalent to the union of criminal and lawful. So this is again an equivalent class. So it means that if something is criminal or lawful, it must be a person. So we're not going to assign criminality or law-abidingness to animals, which one could argue you could, but I don't know if you can arrest animals. Yes. You can put them down, I guess. You can put them in detention and
legally speaking, some animals have been arrested and sentenced and executed.
Yeah, so I know some animals are taken off the street and put down, they're attacking people and so forth, but yeah. Okay, so if that's the case, we shouldn't define this. We could define this as rather some living being or something, but okay. So we have criminal or lawful is equivalent to person. So we have person subclass of criminal lawful, criminal or lawful subclass of person. Person equivalent class union of criminal lawful here. If we say that Vincent is lawful, what could we assume? What can we conclude? Sorry. Yeah, Vincent's a person. Yeah. Okay, maybe not so interesting, but what if we say Vincent is a person? Yeah, exactly. Yeah. So based on this, we have to decide Vincent must be criminal or lawful or both. Yeah, so we've still not said that they're disjoint. Yeah. So we know from this that Vincent, and there's no good way to write this down. We could write it out in OWL, but it would be very long. Vincent must be either lawful or criminal or both. We don't know which. We don't know which of the three cases, but we know that Vincent must be in one of these classes, could be in both. If we want to exclude the both case, there is another feature called disjoint union of. Yeah. So disjoint union of is sort of like a union, but I put this D symbol here just for short to indicate that in this case, Vincent must be criminal or lawful, but cannot be both. Yeah. So it's a shortcut for stating that for excluding the both case. Yeah. So Vincent is either criminal or he's lawful. We don't know which, but since he's a person, he must be one of these two, but not both. We can define classes based on the negation of other classes. So we can define a new class here, which is all the things that are not alive. Yeah. And we can say that that's equivalent to dead. Yeah. So what would this mean? It means that, let's say we know that Mary is alive. What can we infer? Not dead. Yeah. So you can say, okay, then Mary is not dead. Spoiler. He died of old age. It's okay. Natural causes. Vito is dead. Old age. He had a long, happy life. It's okay. Vito is dead. What does it mean? Vito's not alive. Yeah. So this is the long, awkward way of writing Vito is not alive. Yeah, it's kind of a bit ugly, but okay. We have one of, so we can define a new class. This is our class definition here, where essentially we define all of the entities that make up that class. Yeah. So it could be useful. This example is maybe not so nice, but there's other examples. We could define all of the regions of Chile and name all of them, or all of the US states and name all of them, or whatever. Class has a small-ish set of instances that define it. We can define a class in that way. So in this case, we're defining Godfather to be precisely equivalent to the class with 3 elements: Vito, Michael, and Vincent. Yep. So what can we infer from this? Not so interesting, but we can say that each of these elements is a Godfather. Yep. So this part is, well, it's okay, fine. What's perhaps more interesting, we'll see, it's at the end of the class. We'll see another example later that involves this. So essentially, the interesting thing is if we know something is a Godfather, we know that it must be equal to one of these, same as one of these entities. So this is one of. Next, we're getting into some first order logic, quantifiers. So we have 2 quantifiers that we'd like to use. One is the, does anyone remember what this means? For all, yeah. So it's like an all, it's an A turned upside down. That's how I remember it, right? So A for all turned upside down, and E for exist turned sideways. Person is a subclass of this class definition here. And this class definition here says this is the class of all entities whose parents are people, are persons. Yeah. So if an entity, if all of the parents of this entity are people, are persons, then that entity will be part of this class here. This is a class whose again, whose parents, all of their parents are persons. Yeah. So basically we're saying that if you're a person, then all of your parents are persons. That's what we're stating. Yeah. Okay. So if we have Mary is a person and Mary has parent Michael, what can we infer about Michael? Michael is a person. Yeah, exactly. So we have Mary type person. Mary has parent Michael. So if we know that all persons have, if the parents of all persons are persons, then it means that Michael must be a person too. Yeah. So we see the definitions here. We have person subclass, and then we have our class definition using a blank node. All values from person on property has parent. So this is all values from. So this is using subclass. One might say, what about equivalent class? No, if all of your parents are people, that makes you a person as well, right? In the other direction. Is that the case? If all of your parents are people, that makes you a person. Anyone think of an exception or a problem with that? If all of your parents are people, then you're a person. Seems okay. However, there is a nasty case. What if you have no parents? What if you're a lawnmower? Then all of your parents are people because you have no parents. So if you have no parents, you, in first order logic, you satisfy this condition, this for all condition. So if you have 0 parents, then all of your parents are whatever, because you have none. They satisfy the for all condition. So for that reason, we have to be a little bit careful. So if we were to state that these were equivalent, that this implies this and this implies this, then we would run into this problem, yeah? Which is that we have choppy. Choppy is an instance of lawnmower, and lawnmower doesn't have any parents. That's what it says. If you're a lawnmower, you don't have any parents. What can we infer now? We can infer that choppy is an instance of this class definition here, which means that Choppy is a person. So we don't want to define this in general, right? So again, if we say, if this class here refers to all the things where all of their parents are people, are persons. If we have something that has no parent, it's in this class. All of its parents are people because it has no parents. So it's trivially true. So this is a little bit counterintuitive. So we need to be a little bit careful. In particular, it's very rare that we're going to say equivalence in this case. It's much more common that we're going to use the subclass towards all values from. It's not that common to use the subclass the other way or to use equivalence with this. Does that make sense? Yeah? Okay, that part's a little bit weird. So there's an explanation here as to what that is for the reference in the slides. But yeah, because Choppy has no parents, Choppy is all of Choppy's parents are people, and that means that Choppy is a person according to these definitions here. So if we have all values from, you might expect to see the other symbol, the other quantifier from first order logic, or from logic in general, which is the backwards E for exists. So we have parent is equivalent to exists has child person. This is fairly intuitive. It basically states that a parent, okay, in this case, we're using it for a human parent, I guess. A parent implies having a child. Yeah, so a parent is equivalent to having a child that's a person. And here, I guess we're implicitly assuming human parent or person parent. And that whatever has a child that's a person is a parent. Yeah. So this seems relatively intuitive from a general perspective. So if we have Michael has child Mary and Mary is a person, what could we infer about Michael? It's a parent. Yeah, so Michael is a parent. What could we infer in the other direction if we had Michael a parent? So what could we say about Michael then? Has a child, yeah. And that child is a person. So who's the child though? We don't know. So we can use some sort of existential element. So this would be, for example, in RDF a blank node. We could say Michael has child and a blank node, and then that blank node is a person to represent the fact that we know that something exists there, but it's not necessarily we don't necessarily know the identity, or we're not necessarily able to identify that that child. So Michael has child, some blank node type of person. Yeah. So
automatic difference, which is different.
I'm sorry?
Is this an automatic difference made by the system?
Yeah, it can be, yeah. So in some systems we'll generate blank nodes to represent these existential identifiers. We're getting into very I mean computationally we're getting into dangerous territory with this. So we can there will be an example later of this, but we're already getting into something that's kind of a little bit dangerous because we're creating new things. There might not be something to curtail how many new things we generate. Yeah. So we have a similar feature, and there's often confusion between some values from and has value. Okay. So has value, what we can basically state is that a certain class, we can define a new class, which is the class of entities that have a particular value, one value, for a particular property. So this definition here states that this is the class of all instances whose species is Homo sapiens. Yeah. So what we're going to say is that a person is a subclass of this class, which is the class of things that have the value Homo sapiens for species. If we say that Mary is of type person, what could we infer now? Mary has species Homo sapiens. Yeah. Okay. We're going to change this and we're going to make this equivalence because it seems to be equivalent. Should be equivalent in all cases. At the moment. Seems relatively safe to say that. If we say that Mary has species Homo sapiens, what can we say about Mary? Mary's of type person. Yeah. Okay. So we have has-self, another type of class definition. In this case, we're going to define the class of all of the entities that love themselves, that have a reflexive loves relation. Yeah. So we have a narcissist. I don't know if there's narcisista. Does that work in Spanish? Yeah. Narcisista. So narcissist is a subclass of loves themselves. Yeah, of the class of things that love themselves. So if Michael is a narcissist, what can we infer about Michael? Michael loves himself. Yeah. If we define this as equivalence and we define that Michael loves himself, what could we infer? Michael is a narcissist. It's a very strong political claim that everybody who loves themselves is a narcissist. I don't mean if you love yourself, I'm not calling you a narcissist. It's all right. And we have two classes of definitions to finish. We have cardinality restrictions, two different types. So the first type of cardinality restriction, we can define a class with a given number of values for a property, and we don't care about what those values are in particular. Yep. So we have exact cardinality, where we say that a person is a subclass of those things that have precisely two biological parents. So this is our class definition here, the class of entities that have precisely two biological parents. Then we're stating an axiom that person is a subclass of this class here. So we state that person is a subclass of this class definition here, which is the class of things that have exactly two biological parents. Yeah. Seems relatively safe to state. I don't know of exceptions to this, but maybe they exist. We can define a maximum version of the cardinality. So we can say, for example, that a monogamist is a subclass of the things that have at most one current spouse. So if you're a monogamist, it means that you can have at most one current spouse. Yeah. So a monogamous subclass of max cardinality 1 on property has current spouse. Yeah. And we can have a min version. So we can say that a parent has at least one child, which is essentially equivalent to some values from. Well, not quite actually. Sorry, forget that. Not yet. So we can say that a parent has at least one child. Yeah. So we say parent equivalent class to something, this class here that has at least one child. It would be equivalent to some values from if we use the top class. I'll come back to that. We'll see a different example. It's very similar to some values from. So we have these three different types of cardinality restrictions. We also have qualified cardinality restrictions where we only count the values that are in a certain class. Yeah. So we add an extra level of detail, which is the class of things that we're going to count as values. Okay. So for example, a biped. A biped is something with two legs, but your arms don't count. Yeah. So you have two legs, but your arms are not counted. So we're going to say that biped is equivalent to the class of things that have two limbs that are legs. Yeah, so we're only going to count the legs. We're not going to include the things that are arms. Yep. So in this case, biped is equivalent class qualified cardinality 2 on property has limb on class leg. Yeah, so we only count in this case the things that are legs, and we forget all the other things. So in this case, we're going to define a new class, which is the things that have at most one current member that is a godfather. Yeah. So we're going to say that a mafia is a subclass of this class. Yeah. So what does it mean? It means that a mafia can have lots of current members, but at most one of those members can be a godfather. Yeah. Or a current godfather, we could say. Yeah. So we have this definition here, mafia subclass of this new class definition of all of the things that have at most one current member that is a godfather. Minimum. So in this case, we have a twin, and we're going to say that a twin is a subclass of this class definition here, which is the set of things that have at least one sibling that is a twin. So what are we stating? We're stating that if you're a twin, you have at least one sibling that is a twin. Gemelo. So you can have more siblings, but you can have at most one sibling that is a twin, but you must have at least one sibling that is a twin. And this then is very similar to some values from. When this is set to 1, this is equivalent to some values from. Yep. But we can also have mean qualified cardinality of 2 or 3 or 4 or 5. Yeah. So any questions or doubts about that? We've covered the whole language. Slides are examples, not definitions, just to mention. So we'll look at how to define things in the next class. We're going to talk a little bit more about how to be a bit more formal about what these mean. So the goal today was to illustrate the language. So for example, in this case before, what we saw was that when we saw this example before, we said, okay, this means that Vito is a godfather and Michael is a godfather and Vincent is a godfather. But really, that's not what this is defined as. Yeah. What do I mean? I mean that there can be other things we can conclude from the things we haven't seen in the example. So for example, if we know that Vito Young is a godfather, what could we say about Vito Young? We have some additional information, right? So Vito Young is a godfather, and godfather consists of precisely those 3 entities. What can we say about Vito Young?
He's one of those.
Yeah. He's one of those then. So we know that Vito Young must be the same as one of these entities here, as Vito, Michael, or Vincent. So Vito Young must be the same as Vito or Michael or Vincent. So there are kind of other implicit details that we haven't seen from the examples, and they only come as a result of a formal definition of what these features are. Yeah. So we'll see that the next time. So returning to our zebroid, yeah, we can define now using these language features all of the things about the zebroid that we needed to define to conclude that C is a zebroid. So we're gonna see. So yeah, we've now covered that a zebroid has exactly one parent, a zebra. We've covered that. We've covered that a zebra has exactly one parent, a not zebra, and an equine. This would be the intersection of the complement of zebra and equine. And then we define this with an exact cardinality constraint. Exact qualified cardinality constraint. The subclass of we had before, an equine has exactly 2 parents. That's a qualified, that's just a cardinality constraint on equine. 2 things cannot be related by sire and dam at the same time. That would be a property disjointness act. Right. So we can cover all of these definitions to get this sort of inference now. So as mentioned, yeah, OWL is a much richer language. It has a lot more features for making definitions, claims, and these are used to create what are called ontologies. Yeah. So ontologies are sort of formal conceptualizations of consensus in a domain. So we can use an ontology to say, when we talk about medicine, this is what we mean. Yeah. So when we write or create data, we all will conform to the same ontology and use this to interchange data. So OWL has been heavily used in particular in different settings, but one of the main successes has been in biomedicine, in biomedical ontologies. With this main use case that people need to be precise when they're exchanging data. So you have different ways to describe different things in different regions. So biomedical ontologies are used to define clinical concepts, to reason about them, to classify, to detect inconsistencies. And in that sense, OWL has been heavily used there. It's also been heavily used for the web, but mainly it's more the lightweight features, not the class definitions, but like more the property axioms and so forth are more used there. Yeah, so any questions or doubts? Okay, so in the class or in the lab on Wednesday, we're going to start with the property axioms of OWL. We're going to take the lab bit by bit. So we're going to do first the property axioms, then we're going to look at some class definitions and class axioms, and then we're going to look at some more complex examples so we're going to have 3 labs on OWL. The next 2 classes on OWL, we're going to talk more about theoretical aspects of OWL. We're going to look first at how to define OWL, how the semantics of these sorts of things are defined, like how do we formalize this language. And we're going to talk about computational kind of limits or restrictions of what we can do with this sort of language. So can we actually create algorithms to do this sort of reasoning? So they will be more theoretical topics in the next two classes. And yep, so the lab on Wednesday will be property actions about. Questions or doubts? No? Okay, so see you on Wednesday.